Welcome back to UBC CS 532W, Intro to Probabilistic Programming at the graduate level. My name's Frank, and today we're going to do a second lecture on sequential Monte Carlo. And maybe, I doubt it, but maybe get to inference starting the next lecture on inference in the higher order probabilistic programming language. Okay, so where we left off last time should make it possible for us to read this. Jason, it's really unfortunate that you're suppressing yawn already at this point in the lecture. It's it should make it possible for you to read this pseudocode and understand what's going on. We're going to go through this again, and then we're going to use sequential Monte Carlo inside of a Markov chain Monte Carlo algorithm. So if it doesn't land again right now, I think you're going to get 3 repeats, but we'll just go algorithmically through this again. So what is sequential Monte Carlo? It's a method for sampling from some distribution, or estimating some distribution p hat of x1 to t given y1 to t, and we can set up a sequence of distributions that sequential Monte Carlo samples from differently, and you'll see this later on. But the main point is that you can think state space model, and you're going to get an estimate of this joint posterior distribution out of sequential Monte Carlo, right? And it's recursively important samples, then resamples, and then important samples, then resamples, so on and so forth. So at the initialization, at time 1, the vanilla SMC algorithm, or bootstrap filter, where you sample from the prior, says sample x1 I for some number of particles n, capital N. So this is going to be, there's actually in all of these things a for I equals 1 to n loop, really. But when you see sample xi from mu xi1, you should just read that as sample iid from mu n times. And then set our estimate of the posterior distribution of x1 given y1. And remember that we're in this state space modeling context where we've got x1, x2, x3, y1, y2, y3, like so, and these are observed. So set our estimate of this distribution to be a set of weighted particles where the particles have been drawn from mu, and there are Dirac atoms sitting at those locations, weighted by a likelihood G evaluated at that particle value given the value of the first observation yi. Okay, so we have this intermediate distribution result p tilde. And what we do is we resample a uniformly weighted sample from this conditional distribution estimate to obtain an unweighted particle set, which is just, again, a sum over n, 1 over n of a bunch of atoms that were originally distributed according to this atomic measure. So basically you do some sort of multinomial resampling or something fancy, or stratified resampling, whatever. This gives us our estimate of this posterior distribution of x1 given y1. And then from for t greater than 1, we push our samples forward by basically proposing from the likelihood, which, again, just to be clear, this is f, I'll remind you, this and g. Push our samples forward through the likelihood. So these are the atomic samples that make up the estimate of x1, p of x1 given y1. For each of those, we sample a continuation, and we construct a vector data structure which simply concatenates the new value onto the sequence of old values. Okay, so this is a vector that grows, right? And this is a sample then, or an intermediate result, an intermediate result that needs to be weighted. X tilde I, so there's going to be n of these, and this is a sequence of x's from 1 to t. Then we compute a weighted estimate of the posterior distribution of x1 to t given y1 to t by summing over the weighted by summing over a set of weighted particles where the weights correspond to the fractional weight. The update weight corresponds to weighting by the likelihood, which is just to accumulate this next likelihood term, and then normalizing. Okay, so this hides a normalization. So the unnormalized weight is just this, and then we sum over all the particles to get normalized weights. Then we resample using multinomial or whatever samples to obtain an unweighted final approximation to the posterior distribution of all the x's up to a particular time, given all the y's up to that time. And that, of course, is just an unweighted measure, or a measure of consisting of an equally weighted set of atoms, a probability measure consisting of an equally weighted set of atoms. And that forms our posterior distribution up to t, and this is recursive, so you just run this until you hit the end of your sequence, whatever that happens to be. Okay, everybody remember this? Everybody's cool with this? Remember how we got here? Okay, great. So we'll say a couple of things. The output of sequential Monte Carlo are several things. One is a weighted particle set, so at the final iteration, you can either keep the weights and have lower variance Monte Carlo estimates by computing weighted Monte Carlo estimates, or an unweighted approximation to the same posterior distribution. Okay? So you can have a weighted set, a weighted measure, an unequally weighted atomic measure, or you can have an equally weighted atomic measure that both represent the same distribution. So you can use these for Monte Carlo integration or Monte Carlo estimates, where you integrate against this posterior distribution. And it's very straightforward because we have atomic measures, and those atoms just plug in wherever you would do an integral for marginalization or posterior predictive inference or whatever. Yes, Marin?
Sorry, yeah, just to clarify, the top line here is before resampling, the bottom or the second line is after resampling, right?
Correct.
Yeah, okay.
Yeah. And we get a marginal likelihood estimate. And again, because apparently I never used the word before, marginal likelihood and evidence are the same thing. So when I say evidence, we're going to get an evidence approximation, which is equal to the product over all the time steps of this quantity, which is the product over the average of the unnormalized weights computed at that time step, or that iteration of SMC. Okay. When we talk about RL as inference, this is an interesting object. This will be the total reward achievable under all possible paths through the world. Okay. Cool.
Right,
so what does this look like? We went through this like this much at the end of last lecture. So in systems like linear dynamical systems where we can compute quantities like this posterior distribution P of x1 given y1 analytically, we can plot that. That's going to be this, this blue line. So there's, if you orient it the other way, you can see this is a density on this is basically X space here. So state equals X. This is going to be X space. Okay. So this is P of X1 given Y1. And the SMC estimate of the filtering distribution, mean. That's this quantity. It's going to be this little dot right there, right? And the particle approximation to this, which is going to be the stuff over here. Good so far? Okay. So what SMC does, so we have a particle approximation to this. Now we update this by running it through the process that we talked about. So we sample forward under the bootstrap filter from the prior, basically the likelihood. We run the program forward. And then we accumulate the observed likelihoods, and then we reweight and resample. And what we get then is, so again, as before, this is this curve, this is this curve. In other words, these are the true filtering distributions, right? These are the SMC estimates of the same, and they're plotted in these red circles. So circle, circle, right? And a particle approximation to the joint distribution here. Okay, so the joint distribution is, an atom which consists of something like this, and an atom that consists of a pair like this, so on and so forth. So we have paths. So if you think about what the samples from this joint distribution are, they're going to be pairs of X values. Yeah. All good so far? Okay. And we can keep going, okay? All right, so this is effectively sequential Monte Carlo and some kind of dynamical systems model. It doesn't really matter what it is. We don't know what it is, but the point of these figures is to show a couple of things. One is that as sequential Monte Carlo continues to run, by simple virtue of the fact that every time you do a resampling, you choose not to continue some of the trajectories. So here we can already see that if you look at the sample diversity of the first set of X values, right? They go from minus 1.6 to 0.4. Already some of them are being cut off, right? So there were values basically all the way up here, and there were values all the way down here, and values in between. Those have been thrown away because they don't explain the data well. They've been resampled away, right? So there are n particles here, but there are less than n particles, distinct values here. So a particle is a complete trajectory, but the number of distinct values is going to go down. And it will continue to go down, and it will continue to go down, so on and so forth. Okay. And this leads to something called particle degeneracy.
That's a good question.
Mm-hmm.
So how come, like, it looks like you go back in time to when you delete them, you remove them from the past. Why don't you just remove them from your point on into the future?
Because the computation that's being done when you're resampling is to concentrate computational effort on those particles that well explain the existing data. Right? So you can't remove futures, and in some sense you are removing futures. But the net effect of removing futures or select it, like, so yes, you are removing futures. That's what you're doing. You're saying, okay, the particle, like straight away, any particle that started here may not have children. It doesn't make any sense. It doesn't explain this observation well. Or we don't actually see the observations, but it didn't explain the observation. We know for a fact that it didn't explain the observation well because it's very far from the posterior probability. And particles that explain the observations well have high posterior probability, right? So this one, no children for you. So we're removing all of these futures, but by removing all of these futures, we are effectively eliminating the number of particles that can continue to have that can have children. So we have entire lineages that are killed off, right? And that's what's happening. So you get here, and at some point, there was a path that went here, and there was a path here, but they got killed off. And there was a path that went here, and there was a path that went here, but they got killed off.
But they only get killed off from that point forward, right? Like you don't go back in time to sort of eliminate their ancestors too.
That's correct. But the point is that SMC targets and actually builds a representation of this posterior distribution. And at the end of the day, this posterior distribution is going to consist of a set of particles whose diversity is large at the end and whose diversity is small at the beginning simply because of the resampling step. So there are existing in, if you choose to, there are existing in memory all kinds of paths here, but they are invalid with respect to sampling from this posterior distribution.
So is it just an artifact of how it's being plotted that those don't show up after they've been killed off?
It's an intentional artifact of how they're being plotted, because if you think of those things as existing, they are totally irrelevant for estimating or representing this posterior distribution. They are literally just wasted computation. In some sense, for those of you who are interested in like evolutionary algorithms and these sorts of things, the sequential Monte Carlo process actually looks a lot like evolutionary algorithms, where you have some set of particles whose fitness is being evaluated all the time, and those whose fitness is high, they get to keep going, and those whose fitness are low, they die, which means that their entire lineage is no longer represented in the posterior distribution. Okay. Cool.
Are there like variants of that are kind of more like Dijkstra's algorithm, where you maybe keep some paths not of the current length if they're not if you keep some paths of the shorter length that are might be promising for some reason, and if your like future paths have all like low
Thank you for asking this question. I get to point you to one of the least appreciated but really, really cool outputs from my Oxford group, which is the asynchronous SMC, or the particle cascade. So the issue, though, is that when you do something Dijkstra's like, you have to, or whatever. I understand what you're getting at. Like, you would really like to say, oh well, you know what? Actually, it turns out that all of these paths enter like a probability zero region of likelihood.
Yeah.
Which means that you really, really, really want to be able to backtrack and start something back here, right?
Yeah, exactly.
The issue is that resampling is a synchronous activity. In other words, you have to actually have all of your particles arrive so that they're correctly weighted so that you can synchronously choose to continue or not. And as soon as you try to do something Dijkstra's like, you have to relax this synchronicity requirement. And relaxing the synchronicity requirement leads to an entirely different algorithm which is still sequential Monte Carlo. Right? It leads to a completely different algorithm for basically resampling. And yes, this exists, and we call it the particle cascade, and it was runner-up for Best in Europe's paper in 2017 or something like that. 2018, 2016, I don't know, something like that. And it remains vastly underappreciated, particularly if you want to do RL type stuff. So there, a project, dumb project, but a project would be, okay, implement the particle cascade for probabilistic programming. We actually never bothered to do it. But that was why it was designed, actually, exactly for this reason. There's many other variants that can be mixed, matched, and combined to lead to just totally crazy algorithms. Really nice question, thank you. If you ask me later, I can give you an explicit reference to the paper. So empirically, this bootstrap vanilla SMC strategy performs well in terms of estimating all the marginals, right? And in many applications, particularly tracking applications, when you're just asking what the current state of the system is, this is usually good enough. So you can use this for tracking maneuvering vehicles or tracking maneuvering targets if you have a decent model of what's going on. So using this for, unfortunately payment's not here, but using this for doing computer vision where you have a model of how agents move around or something like that, and doing inference, sequential Monte Carlo is the way to go when you have a nonlinear dynamical systems model, period. It's the only way to go. Ryan has some experience doing this with crazy biological systems models that are non-differentiable and nonlinear. Great. Unfortunately, the joint distribution, as you can see, because of degeneracy, is often poorly estimated when t is large. So, in the previous example, when you just look at this, from time step 11 back, our marginal distribution, our marginal posterior distribution is Dirac. It's an atomic measure on the single sample, right? And there's this degeneracy problem, which is stated formally, says that for any k and for any n, there exists some time such that for any time greater than this tkn, the marginal posterior distribution is Dirac. Okay, so in other words, basically, the marginal distribution, the full posterior distribution, is an unreliable approximate or a very high variance estimate of low variance, high biased estimate of the true marginal posterior distribution as t gets large. This is just saying degeneracy. But there are some really cool convergence results, and these we have used again for model learning in the form of AESMC and a family of papers that are very similar to AESMC, which is to say that the marginal likelihood estimate is unbiased. So in expectation, so in other words, if you run the particle filter many, many times and estimate the marginal probability using the product of the average of the unnormalized weights, this gives you an estimate of the evidence. Okay, and again, the really cool thing about this, we're going to see two reasons why this is cool. One in this lecture, and then depending on where we get in the course, we'll see another version of this. At the end of the day, if we're doing point estimation, there's going to be some model parameters here, right? And we might wish to learn those model parameters as point estimates, which means that we want to actually maximize the evidence with respect to those parameters. And having an unbiased estimator of the evidence is quite useful because you can directly optimize the model under this objective. Okay? Fine, and there are a bunch of other formal statements that you can make, which, if you get into proving, correctness of and asymptotic properties of sequential Monte Carlo algorithms, become relevant. If you're interested in how to prove this, my former student Tuanan has the best notes, I think, on how to prove the unbiasedness thing. We could spend literally an entire lecture just proving the unbiasedness result for the sequential Monte Carlo estimate of the marginal likelihood. We could also spend an entire lecture or half of a term on better resampling schemes for sequential Monte Carlo. I'll just name a couple. There's a bunch of them. That's really, I spent a bunch of time doing this work, and it's really, I don't think at the end of the day all that important. There are different ways of resampling to get an unweighted particle set, and they can have large impacts on actual performance in reality. A couple of named results are residual resampling and systematic resampling. A systematic resampling is kind of fun if you construct the empirical CDF of the weights. That's a terrible thing to have made them all the same. Here are the weights, you know, weight 1, weight 2, weight 3, something like that. You can sample instead of doing multinomial resampling, you can say, I want n samples, and the way I'm going to get it is I'm going to construct an equally spaced ladder of length n, where each bin is of size 1 over n. And what I'm going to do to sample from this empirical CDF is sample a 1 over n size offset uniformly in here, and then just put the ladder down and pick whatever falls in these bins. Okay. This gives you a very it gives you a very different probability of choosing low probability samples that still has the required expected value in terms of the number of continuations as a function of the weights. Okay, and there's a bunch of these, and there's a really nice paper with some beautiful figures. If you decide to go down the SMC route, and the SMC rabbit hole is a very interesting rabbit hole to go down. There's an awesome paper here that talks about different resampling schemes and their computational costs and their benefits and that sort of thing. One more thing, when you're running sequential Monte Carlo, resampling is clearly good because it concentrates computational resources, but it's also clearly bad because it leads to degeneracy, as we've just discussed, right? So you don't want to resample too often. And really, you want some measure of when to resample. So in other words, you don't have to resample every time. You can just keep accumulating weights and accumulating weights until whenever, right? And one way to do this is to use what is called the effective sample size, which is effectively a kind of a measure of the variance of the weights. So if you look at this, this is the normalized weights. If you set 1 over n in here, this is then the sum of, sum I equals 1 to n of 1 over n squared inverse, right? Something like that. I got n copies of it. So this is, n, right? So if the unnormalized weights are uniform, which is to say that you have uniformly weighted samples, after you apply the likelihood, which can happen, and I'll explain how this can happen in just a second, then the effective sample size is n. It's like you have n independent samples, and when you're computing, you compute with effectively n independent samples. However, if one of the weights dominates and all the rest of them are 0, then the effective sample size is 1. If you just look at what happens, you put 1 in here and 0 everywhere else, and you get 1 squared inverse is 1, and 0 squared is 0, and you sum it up and whatever, okay? So a very nice result showed that for simple importance sampling, for nice test functions, the variance of the Monte Carlo estimate under a weighted particle set looks like the variance under the true posterior distribution, of an empirical average related to the effective sample size. In other words, the estimate that you get is out of an important sampling scheme. SMC is an important sampling scheme, is roughly as accurate as using an IID sample of size ESS from the posterior distribution. Okay, so we want to keep ESS as high as possible, but we don't want to resample so often that we unnecessarily introduce particle degeneracy. So I forget what the target is. Usually you target like an ESS of like n/2. I think maybe that's on the next slide. Yeah. So a typical thing to do is to monitor ESS as you're going, which is obviously an easy thing to do. You just, like keep track of your normalized weights and compute ESS as you go. And if ESS drops too much, in other words, you're like wasting half of your computation effectively, your effective sample size is n/2, then resample. Okay. So when you do your probabilistic programming interpreter in homework 6, a very reasonable thing to do is to have runtime checks on addresses to make sure that you arrive at the same observation for resampling, and then only to resample when the effective sample size drops below n/2, where n is the number of samples here. Okay. You can also look at the entropy of the discrete distribution, so on and so forth, and then trigger resampling based on that. Okay, so how do we improve the sampling step? So we just basically talked about a bootstrap filter, right, where we sample the particles blindly according to the prior. We don't take into account the observation. So what we can do, just like in important sampling, is we can introduce an arbitrary proposal distribution. And here we're just going to look at proposal distributions that look at the current time step y. In Prog and in inference compilation and so on and so forth, we're going to think about proposal distributions that take into account the full sequence of observations, but that's actually a little bit dicey, so we're just going to go with what's standard here. So if we have the ability to either learn or compute some proposal distribution that's close to this quantity, which is the posterior distribution of x given yt, then, well, we can use it in important sampling. So we know that the recursion breaks down like this, right? We have the posterior distribution up to t minus 1. Here we have the posterior distribution up to t. And effectively, the proposal distribution says sample from F, weight by G, and then renormalize, right? Clearly, we can sample from Q and weight by W, because if we replace this W in here, we get back exactly what we had here. So if you're okay with this recursion, then if you substitute this W in right here, the Q's cancel, and you're left with exactly the same thing. You have G and F on top and P on bottom, and you're done. Okay. So this suggests a more general sequential Monte Carlo algorithm, which is to say that you can sample or run your probabilistic program from something other than the program itself. You can learn to run the program from a proposal distribution instead. Okay, fine. Okay, and what does it look like? Well, a more general SMC algorithm says we have n weighted particles approximating blah 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 at time t. Right. Note that these are weighted particles now, right? At time t, we sample x from Q. We do the same data structure thing we did before, right? We have an empirical, this constructs an empirical measure, right? And the weights that we maintain are not the same weights that we did before, but instead our weights are F times G over Q. So long as you can evaluate this Q, then you can string along a set of weights, and that's fine. If the ESS falls below some threshold, then you can resample, set the weights equal to uniform weights and get an unweighted estimate up to that point. That make sense? Questions here? Even a question like, what's the point, is fine.
Sure.
Sure is not a question.
I mean, yeah, why would we not sample from F, basically? Yeah.
Because F is the prior, and it may be that the particular set of observations, that a particular observation at a particular time step says actually the true value of X at that particular time step is very unlikely given that observation. In which case you would really rather sample from the posterior or something like the posterior or some proposal distribution that is not the prior, that makes use of the fact that the observation tells you something different. What I was thinking about when I paused was whether or not to go down the algebraic rabbit hole of another way of seeing it is that this is P of xt yt, which is proportional to P of xt given yt. That's the whole point of what's happening here. And if you use a Q that is very close to this, then the weights that you encounter are that you add are effectively 1 up to a constant factor. And I don't want to get into there's not enough space to do it. I don't want to get into the fact that this is equal modulo a P of yt factor, because then that yt goes into the denominator in a complicated way. Does that make sense? Effectively, this is proportional to the posterior. So if you could propose exactly from the one-step posterior, all you would have is a constant weight, which means that all of your particles would be multiplied by the same constant weight. And then when you normalize them, they would all be equally weighted, in which case you have maximum effective sample size. And this is relevant when we talk about inference compilation and we use the entire set of observations. Very relevant. There's another project idea. Okay, so if we, I guess, yeah. So that's basically what I just said. Amazing, beautiful. Our aim is to select a proposal of this form that is as close as possible to the posterior distribution, because that minimizes the variance of this quantity, which is exactly what we just talked about, right? This is the joint, which is proportional to the posterior, which means that the weight is uniform if it's true, if this Q is equal to P of xt given yt, I did not do the xt minus 1 before. I apologize. I forgot about the xt minus 1, but whatever. Same deal. Make sense? Okay, got a few nods. All right. So a useful exercise and an interesting project, just to throw it out there, is to say what happens if you adapt Q, if you could do this. If you could use a Q of this form. This is no longer this using a Q of this form will no longer guarantee minimum variance weights, because you will have extra terms up here, basically. And the extra terms up here, by the way, are going to be related to the Q function from reinforcement learning. Okay. This will come, but I just want you to foreshadow what's happening. Okay. And we can only introduce these via heuristic factors, which I don't think we'll talk about in this class, but it's worth mentioning that that SMC with heuristic factors is something that probabilistic programming has put out there. So nobody's actually really wired it together in a nice, clear, clean paper, but there's a beautiful, beautiful thing sitting just outside the current literature. Okay, this is a great place for a pause. Actually, for once, it'll be close to the middle of class. So let's take the fully anonymous backwards memorial carbohydrate and pee break, and be back at 4:23. Please. Welcome back. So we just got done talking about proposals. Now for something completely different. Let's imagine that we're doing model learning or optimization or inference in a model that looks like this. And for those of you who are working on memory-like models or whatever, and don't care about differentiability, your ears should perk up now or whatever. Okay, let's pretend we're doing a model like this, right? What might you want to do with theta, right? So theta would be some sort of fixed parameter that governs either f or g or both. It describes either the simulator or the observation model or whatever, right? There's a whole bunch of situations in which you can imagine models like this. But basically, you can think of theta as being a parameter that governs the evolution of the state space model in some kind of a way, right? If you have a big nonlinear dynamical state space model or something like that, you can imagine these are the weights of the neural networks that govern both f and g, for instance. Makes sense? So if you had a model like this, you could imagine wanting to, and in fact, you wanted to sample jointly from these two quantities. So you'd like to get the joint posterior distribution. So you're interested in P of theta given x1 to x, I guess we use t here, given y1 to t. So those are all the latent variables, and we'd like to get the posterior distribution of all of those. You might imagine sampling in the following manner, a Markov chain Monte Carlo algorithm that samples in the following way. We propose, so this is going to be a Markov chain Monte Carlo algorithm. In our language, this would be propose, so don't worry about this. So we sample theta star from some proposal distribution, and here I minus 1 is going to be, so this iteration is going to be iteration of MC algorithm. We're going to want to basically write, you'll see where this goes in just a second, but hang with me. So we're going to propose theta star from some proposal distribution on the space of theta. And then somehow magically, we're going to actually sample xt given the value of theta star from the posterior distribution of xt given yt. Okay. Fine. And then with probability, this is the standard Metropolis-Hastings ratio that you should be familiar with right now. You know, we're going to accept a move in theta space by evaluating the joint distribution under theta star over the joint distribution under theta I minus 1, and so on and so forth. Okay. And we have the Hastings correction thing, and now this is just standard Metropolis-Hastings. So please tell me that this looks very familiar and you can understand what's going on here with Metropolis-Hastings. Okay, good. We've established some mutual understanding. Good. Okay. So this is a little bit crazy, okay? This is the kind of like Bayesian thinking, and hopefully for those of you who fall into this now and understand what's going on, you'll start to see how this graphical model thinking, even outside of specifically modeling, but thinking about inference algorithms, can be very helpful, okay? So what this algorithm corresponds to is doing inference in a model that looks like this right here, okay? So we've refactored the model. So we're still in this state space model, but we've refactored it in a very, very strange way, right? So we've said that we have some distribution here, which is P of y1 to t given theta. That's a true likelihood. This is an evidence, right? Or it's a likelihood under a model parameterized by theta, same thing, right? That arises by integrating over the x's. Of course, we don't actually have access to P of to this thing, right? But let's imagine that we do. Okay. If we did, then we would have a model that looks like this, where we have theta and y1 to t. And if we wanted to sample in this model, I think it's fair to say that you should understand that you could run Metropolis-Hastings on simply this part. And by this part, I mean this part. Can you see that? Yeah. Yeah. You run Metropolis-Hastings on this, basically Metropolis-Hastings on theta, right? And then at any point you can generate a sample of x1 to t, because it's in the Markov, it's head to tail with respect to all of the other variables. In other words, you could just sample x1 to t anytime you want from any combination of theta and y1 to t, right? Provided that you get samples of theta. In other words, posterior samples of theta will give you you sample theta, and then you sample x1 to t given those values, right? So that's what's happened. So just to be clear, this part is orange. This part is yellow. Okay, and the insane thing that's happening right now is that somehow we're writing down this Metropolis-Hastings sampler where we're assuming that this thing exists, that we can evaluate this. Which, if you think about what this is saying, particularly when we're in this funny world of state space models, it's saying that we're going to integrate out these things. Right? Any guess where this is going? What's the natural thing that you would do if you, now that you know what sequential Monte Carlo can give you, what's the natural thing that you would want to do here? Uh-oh, I've paused for more than 7 seconds and nobody's given me an answer. Not even Barron. That's bad. Emma, come on, come on. You can do it. Come on. I know you can.
I was just going to say nothing about this is natural to me. So, like, if you want to...
Nothing about graduate school, education,
great.
inference, you know, the pursuit of mathematical excellence, none of it's natural. So, like, that's invalid. Yes.
I'm going to throw something out here.
Awesome.
Could we try doing SMC on theta as opposed to on X?
Okay, you're starting to think creatively. Yeah, this is good. This is not what I'm going for. What are the? I'll give you another. I'll give you all some more hints. What are the outputs of sequential Monte Carlo?
It's the posterior of xt given y1 up to t.
X1 to t up given y1 to t. But there's this other thing that everybody skips over. It seems trivial. It seems, you know, like what the hell's the point of this thing? Emma's even accused me of not actually naming it several times.
The evidence.
Yeah, so what are we going to do with the evidence?
Approximate it?
What if we did, oh man, that's not what I intended to write there.
I don't remember what the hat means.
Okay. So we can get a marginal probability estimate. The hat is that it is not the true marginal probability, right? All we know is that it's unbiased and it has variance and there's a central limit theorem and that sort of thing. Okay. There's the p hat again, right? And it says that unbiased means that when we use SMC, in expectation over many SMC runs, it's going to be the average over those, right, will be the true evidence. Okay. So it stands to reason that if you were to do something kind of seemingly insane, where you want to do parameter estimation in some state space model, right? That you could, like, and this is like so creative that it's a little bit insane. You could imagine saying, okay, well, what if we could, you know, actually have an evidence estimate, right, or if we could actually compute the evidence, then we could do, Metropolis Hastings. We could do, Metropolis Hastings in this model if we could compute the evidence, right? That's going to give us the ability to sample in the space of theta, right? Fine. But, well, why not? Why not? Could we actually use an estimate there? Okay. So this gives rise to an interesting algorithm called the particle marginal Metropolis Hastings sampler. Okay. So if we assume very reasonably that the idealized marginal Metropolis Hastings sampler chain is ergodic, which is to say if you run MH in this model, it's ergodic, right? And admits the this posterior distribution here, right? Yeah, how do I want to say this? Forget this stuff for a second. Just don't even worry about this. Let's just say this. And I know it's this in the next slide that matter. So let U be all the random variables used to build the SMC estimate. Okay, and in particular, what this means is we're going to basically identify all of the resampling steps and the proposal samples, but just really think about resampling. Those are the random variables that sequential Monte Carlo consumes. So there'll be n by t of these random variables, and think about reparameterizing them so they're just drawn from some pseudo-random number generator. Okay, so you just have an n by t source of random variables that you consume. Okay, fine. If we let U be all those random variables that we use in constructing the SMC estimate, then we know that an equivalent statement of the unbiasedness result for sequential Monte Carlo is that if you take an expectation over running sequential Monte Carlo over and over and over again, in other words, if you average over runs of sequential Monte Carlo, which means choose the random variables that you choose in the sequential Monte Carlo many, many times from this queue, right? Then this is a restatement of the unbiasedness condition. So you can prove unbiasedness, but then a corollary to that is this is true. There is a set of random variables out there that you consume when you run sequential Monte Carlo. And this marginalization is exactly the unbiasedness condition. Jason, you're smiling. You getting it? Okay. I guess another way of saying it is when we compute the expectation. I'll just say it in words one more time. When we compute the expectation that states that the expected marginal probability estimate is the true marginal probability estimate, or the expected evidence is that under SMC is the true evidence, what expectation are we taking that with respect to? Runs of sequential Monte Carlo. What's random in sequential Monte Carlo? The choice of ancestors. That's it. The resampling steps.
That's a good question.
Yep.
I got a little confused when you said we're taking the expectation with respect to expectation. Like,
no, if I'd said that, let me go back. This result, which I didn't prove in here, but I pointed you to a place where you could. Oops. this result, what's this expectation over?
The evidence? Why?
It's over all of the internal randomness inside the sequential Monte Carlo algorithm, which is resampling, sampling from the proposals, so on and so forth. In other words, this expectation is about rerunning the sequential Monte Carlo algorithm.
Sorry, so when you say what is the expectation over, are you asking like what is random in the expression that you're taking the expectation of?
Yeah, so if
Okay.
you know, we know an expectation is an integral over something, over some distribution, what and there is some thing that you're taking an expectation of, which is, you know, p hat y1 to t, which is a number, right? So what goes here? And writing it out in all of its gory detail, I highly recommend you look at this. That has it all in its glorious detail. But we know, for instance, that there'll be a product of, you know, t equals 1 to t, a product of n equals 1 to n of q of I'm going to run out of stuff, x ti given x t I minus 1, t minus 1 I, right? And then the multinomial sample of, there's an ancestor in here. We're going to say ancestor here, which is like what it came from. And then there's going to be a multinomial of ancestor given weights for all of those pairs. So this is basically all of the random stuff that happens inside of sequential Monte Carlo. It's the draws from whatever the proposal distribution is, and in the bootstrap filter, that proposal distribution is the prior. Otherwise, you can have a Q. That's what this Q is here. And there are a bunch of multinomial or resampling steps that you draw random indices for your ancestors. Greg?
Yeah. So that is this basically just over all x's and like overall x paths, basically, right?
All x paths and all ancestors. So the entire SMC machinery required to compute the marginal probability estimate.
Okay.
Okay.
So this whole how do you say that statement of this expectation in terms of this sort of SMC machinery, it sounds very complicated, while it seems that the samples that you sort of have at the end of the day, they come from the posterior, right? So like
this statement is not a statement about the posterior. It's a statement about the sampling distribution of your estimate of this number. This is a number. This is like, you know, minus, I guess this is, you know, this is going to be, this is not in log space. So this is going to be, you know, 0.000001763.
So it's the distribution over sort of the normalizing constants that you
the distribution over the normalizing constants that arises from different runs of sequential Monte Carlo.
Okay.
Okay. So this is, you know, this statement is the same as the unbiasedness. This is exactly the same statement. Okay. Here comes the trippy bit. So there's this algorithm, which I suggested, right? So we had this idealized marginal metropolis Hastings sampler. And then I said, oh man, if we could just use estimates here, that would be super sweet, right? SMC gives us such an estimate, but that totally bonkers up metropolis Hastings, right? It's not the right ratio, right? You're computing estimates, so you have no idea whether or not in expectation the metropolis Hastings algorithm is going to do the right thing, right? But this algorithm, particle marginal metropolis Hastings, targets this distribution, which again, if you notice, and this is really important, if you marginalize this with respect to u, what do you get?
The evidence back.
Right? That's what the unbiasedness condition says. Okay? Cool. So now let's do some weird, crazy, magic graphical modeling thinking. Right? So now we have this crazy graphical model. It's the same graphical model we had as before, but now we have one more latent variable u, which is just all the randomness that you use to actually compute the probability of y1 to t, to estimate the probability of y1 to t. All right, the link function, if you want to think link functions, because you know about link functions, the link function for computing this probability is the entire computation graph of sequential Monte Carlo. Okay? Cool. So we know that this thing is proportional to the posterior. So that's totally fine, right? Which means that we can use basically we can do metropolis Hastings using this estimate, this SMC estimator of the marginal probability, okay? Which means that if we choose a proposal distribution for an outer Markov chain Monte Carlo algorithm, an outer metropolis Hastings algorithm, then we can evaluate this probability over this probability with the Hastings ratio. And if we just simply write these quantities out, we plug them in. So this joint is here, this joint is here. Here's our proposal distributions, right? But notice how this proposal distribution is factorized. It's just saying make an independent metropolis Hastings sample for each of these random variables u, because why not? Who cares? It's totally fine, right? Then this cancels with this cancels with this, and what you're left with is this beautiful, beautiful, beautiful thing. And I hope that at least 20% of you are getting this. If I manage to get all of you to get this, then this will be a major success from a pedagogical point of view, which is to say that we can do inference in a model like this about the parameters, theta, by performing metropolis Hastings in a model that looks like this, where instead of having to compute this marginal probability exactly, we can use an estimate from sequential Monte Carlo. Okay. So this algorithm, if you the algorithm that corresponds to this metropolis Hastings acceptance ratio, should be very straightforward now. It says if I want to do inference about the model parameters, I just propose a random walk step in model parameters, and then I run a sequential Monte Carlo to get it an unbiased estimate of the marginal probability for the old model parameters and the new model parameters, where I can just sample, where I just run sequential Monte Carlo. That's what this is. This U star and U. You just run it again, right? And we have the prior on the model parameters. There's a prior on these, and this is an ergodic Markov chain that has the right properties to sample from the joint distribution of theta and x, 1 to t, because we can always go back at any point for any value of theta and sample from this posterior. So we sample from this posterior and then this posterior. i.e. this thing right here. Because this is just a byproduct of sequential Monte Carlo. So in other words, sequential Monte Carlo gives you that already. Okay. Does that make sense? Can anybody understand why this is important or cool?
Sorry, just again, what's the difference between X's and U's?
X's are the latent variables. U's
Okay.
are the random choices consumed in sequential Monte Carlo, of which X's are technically a subset.
Okay. Yeah, I just thought like from previous slide that they're actually like the same thing, but
No,
yeah,
they're not.
Okay.
Because this has the ancestor resampling in it as well. It has the resampling steps in it.
Okay.
So I like how Arnaud says this, but this took me a very, very long time to understand. And I'm not sure that I fully understand it even to this day. But the point is, this is, I guess, what do they call marginal metropolis Hastings methods? Yeah, the trivial, quote unquote trivial, but deep result, which is to say that if you have an unbiased likelihood estimate within a Markov chain Monte Carlo scheme, you do not perturb the invariant distribution. So anytime you can, whenever you need to compute a likelihood or something like that, if you can compute an unbiased estimate of that likelihood, you're totally fine. Okay, so for your tool set of Markov chain Monte Carlo algorithms, this is quite valuable. And maybe kind of more interestingly, right? You can consider the case where theta is the empty set. Okay. And this suggests something interesting, which is that you can overcome particle degeneracy by iteratively re-executing sequential Monte Carlo. Right? And this means that you can use all the particles by the same argument that relates important sampling weights to acceptance rejection in independent metropolis Hastings. So replacing the graphical model, you just empty out this thing. At iteration I, you sample X star from this, and then with probability, so in other words, you run sequential Monte Carlo, you compute the normalization constant estimate, these things cancel. So really all you do is you run sequential Monte Carlo, and then you compute the ratio of the normalization constants, and you set the particle set to the complete particle set of the new run or the complete particle set of the old run, and keep going. And this is the first sequential Monte Carlo algorithm for probabilistic programming. You run sequential Monte Carlo over. So you, in your homework, you'll just do sequential Monte Carlo, but the right implementation of sequential Monte Carlo, or the first of many right implementations of sequential Monte Carlo for probabilistic programming, is to also track the normalization constant and allow sequential Monte Carlo to be an anytime algorithm as well, in which full trajectory traces, sets of trajectory traces are emitted.
So I've heard the term anytime used with algorithms before, but I don't really know what it means. Could you explain that?
It means that you can ask the algorithm to do more computation and improve its result. So when you're doing when you're computing an expectation with respect to a stream of samples drawn from a Markov chain Monte Carlo algorithm, you can always ask for more computation to be used to generate more samples to decrease the variance of your estimate. In sequential Monte Carlo, without what I'm talking about right now, you run n particles and then you're done. That's all you have. What you would like to be able to do is you would like to be able to run more computation and use the strong law of large numbers in the Markov chain Monte Carlo sense to add computation and increase the quality of your posterior expectations in the lower variance, less biased sense, right?
So when it's running, you can say, actually, I want more samples.
Mm-hmm.
Okay.
Yeah, so you just like you pause or yield or whatever, and you say, okay, exactly how you've implemented, or theoretically you've implemented your samplers in Python to this point, right? You can just say, please give me, iterate more, right? And the iterate more here says, give me n more complete trajectories via sequential Monte Carlo. And that is clearly 2 lectures worth of material in these sequential Monte Carlo slides, almost to the button and well organized. So that's good. So what's sequential Monte Carlo? It's a general purpose algorithm compatible with probabilistic programming. It's also used for state space inference in state space models with nonlinear dynamical, nonlinear dynamics and so on and so forth. Bootstrap, the simplest of sequential Monte Carlo algorithms, suffers from degeneracy issues and can suffer from going to bad places early and high variance results, right? Particularly with a small number of particles. Everything is good when you have an infinite number of particles. Advanced sequential Monte Carlo algorithms address this degeneracy. So I gave you the very, very simplest version of one of these algorithms, which is iterated sequential Monte Carlo, where you run sequential Monte Carlo again and again and again, basically treating it as a particle marginal metropolis Hastings algorithm, in which there is no theta. But if you want to do parameter estimation, that's cool as well, or compute uncertainties over latent global parameters. There's a whole slew of advanced sequential Monte Carlo algorithms that are pretty cool. One is particle MCMC. That's the paper. This is the paper where most of these results are found. And there's a particularly challenging result in there called particle Gibbs, where actually you do this kind of a trick where I was talking about in iterated sequential Monte Carlo, but you also condition on a complete trace. So you get a hill walking kind of behavior and an acceptance ratio, which is 1. That one is hairy enough that you just need to read about it. And then there's a couple of others that came out of my group. One is called interacting particle Markov chain Monte Carlo, which basically extends this idea of parallel execution of SMC to a kind of ridiculous but awesome degree. Also really, really interesting if you're into reinforcement learning. And then, Greg, the paper that I was talking about earlier is asynchronous anytime sequential Monte Carlo. So anytime is Emma's new favorite word, which means that here you can inject more particles and just run them through, and asynchronous means that you don't have to actually synchronize at observe or resample barriers, basically. And this one is pretty interesting, and in fact was the basis for probabilistic C. That's where it came from. That's why we wanted to do this. And we will start talking about this when we get to inference compilation and other stuff, but learn proposals in particular have the potential to make sequential Monte Carlo incredibly efficient. So in other words, if you learn a proposal distribution, sequential Monte Carlo can become, like importance sampling, effectively arbitrarily efficient. So that's it, and I'll take questions as always. Thank you for your attention.
So a question that I sort of have is that it seems that at least in a sort of Prog sense, what we tend to do is sort of like the sequence of distributions that we consider is sort of you keep adding likelihood terms, right? Like you keep adding your observations one by one. Well, in sort of
roughly speaking, that's correct. I would say that that's not quite true because of the things that I talked about before, which is that you have no a priori guarantee that the sequence that you will have the same number of observations in all traces, which means that really it's to a first approximation what you're saying is true, but really you should think about it as there are a sequence of checkpoints that you will go through, where those checkpoints you can define almost arbitrarily. They don't even have to be observed statements. They can just be anywhere in the code, basically, so long as the program, all execution traces go through that checkpoint.
So, but how I've seen it formulated sometimes as well is if you just you have some distribution A, distribution B, you take distribution A to the power 1 minus beta and the distribution B to the power of beta, and you sort of interpolate between the two, where one could be the prior, the other one could be the full posterior.
Yes. So
is that something that would be compatible with Prog systems, or is that just infeasible to do because of that power?
No, of course. It's totally compatible with Foppel. It's totally incompatible with Hoppel.
Okay.
Right. In Foppel, you have access to all of the likelihoods that could ever be considered.
Yeah.
Because you've unrolled the computation graph. In Hoppel, you cannot unroll the computation graph, so you cannot do geometric paths or propose some other sequence of target distributions.
So you just sort of have to like take them as they come, basically.
There is really no other choice. Yeah.
Mm-hmm. Yeah. Okay.
So what degree of freedom remains is what heuristic factors can you put on there, and how well can you adaptively learn some sort of proposal distribution. Those are the degrees of freedom that you have in the Hoppel case.
Mm-hmm. Okay.
So this is kind of a tangential question, but you mentioned that the particle marginal MH sampler can do parameter estimation, right? Is this possible with any kind of like complex data, like the deep learning models, or do we still have to rely on like backprop for that?
So let's be clear. Here we're doing inference over this. We're doing full posterior inference, right? Excuse me. If one were to do not full, so let's remember, Metropolis Hastings is like the poor person's optimization algorithm. It's a hill climbing with an occasional hill descending component, right? It's also the dumbest way to do optimization if you have gradients available to you, because if you do have gradients, then you should just use gradient descent, right? So let's be clear about that. But here we're talking about inference rather than optimization per se, right? Yeah, that's the first thing. The second thing is that this quantity, provided that it's differentiable with respect to theta, is something that you could use for inference, or for parameter estimation, right? And this is exactly the idea in auto-encoding sequential Monte Carlo, or in the other variants that were copied from my group and published in one instance slightly before my group, which is very annoying. The idea is that the computation graph of sequential Monte Carlo is nearly differentiable with respect to theta. The only problem is that the resampling step is not. So what people do is they just ignore some of the gradients. So basically, if you just run backprop on the sequential Monte Carlo computation graph, you get a pretty decent gradient estimate for theta. In fact, because it's a tighter bound, as we'll discuss, it's a tighter bound on the evidence than you can get under importance sampling or other mechanisms. You tend to learn very, very good models if you just do sequential Monte Carlo and do gradient descent on theta.
This is probably a dumb question, but why is the resampling step not like differentiable?
That's not a dumb question, and for that we will have to go through some hairy papers like AESMC and the rest. And I'm happy to do that. Or ordinary versions of this course where I decide not to lecture would end soon in terms of subject material, and we would all have to read papers and talk about them. But I'm not sure that we'll get to AESMC. I just want you to hint. I want you to be aware that this is precisely where auto-encoding sequential Monte Carlo comes from. In particular, the idea that there's a marginal probability estimate that you get from sequential Monte Carlo, and that marginal probability estimate is very, very tight. In fact, it's unbiased, and its variance goes down as well, I mean, we have the asymptotics here. We can go back to the asymptotics. Like, as you increase n, the difference between our estimate and the true marginal probability gets very small. Right. So that's very good for deep generative model parameter learning. More questions?
If no one has any question, I have a question about BBVI.
Okay. Yeah.
So the thing is that when computing log of P of joint distribution over Q, our proposal, if we assume that our variables are independent, then we end up with log of W equals log of sum of log of observed variables, right? Am I right?
Depending on the structure of P, yeah, it will decompose. Yeah.
Yeah. So here, if we
in
have
general, the structure of the probabilistic program does not allow you to do that, but you could analyze the graphical model to get into like factors. Yeah.
I think in homeworks we were allowed to do that, right?
No.
No, we weren't. Okay. But if we are allowed to do this, does it mean
you're only allowed to do this if the model structure allows you to do this?
So if the model structure allows us to do this, does it mean that the more samples we have, the more observations we have that are far from our priors, the longer it takes for our prior to converge to posterior, for our proposal to converge to posterior? Or this has nothing to do with it?
There are many intertwined problems here, and picking them apart is complicated. So one is, generally speaking, the posterior will be more sharply peaked.
I think Frank is.
When you have lots and lots of observations, will require deforming Q more when there are more observations. But it entirely depends on what the initialization is for Q, how hard that is to do. So I think really you're asking more of an optimization question than you are asking a question about like the subject of what we've been talking about. Yeah, yes, the optimization problem gets harder in some sense almost always when you have more observations, because either you have to move Q more or you have to decrease its variance somehow more.
And it also has, sorry, yeah.
Go ahead, yeah.
And it also has something to do with how far each single observation is from our proposal results, right? Or
the way you made that statement doesn't compute.
Mm-hmm. Okay, thank you.
Yeah. More questions about today's lecture or sequential Monte Carlo in general? All right, then. Thank you very much for your time and attention, and I look forward to seeing you on Tuesday.